In this video, we'll be talking about the relationship between sets. Let's start off with two sets, set A and set B. So set A has some elements in it, and set B also has some elements in it. We might want to visualize the relationship between these sets and the elements in the sets, and we can do that using a Venn diagram. When we do this, each set is represented by a closed shape. Normally we use a circle, but it doesn't have to be a circle. So we would have a set A. Here we'll make set A red, and then we'll have set B, and we'll make set B blue. What we want to do is we want to represent all the ways in which elements can be part of A and part of B. Now, some elements may be only in A and not in B, or maybe the elements are only in B but not in A, and we would then use those moons on either side of this diagram. Or maybe we have some elements that are both in set A and in set B, and we would put those in the middle of these elements. Now, we also need to be aware that there may be some elements that are neither in A nor in B, and so they need to live outside of those two circles. Let me now pass this over to my colleague, who will be introducing some more definitions.
We have two new definitions now. The first one being the union of two sets. And if we let A and B be sets, then the union of A and B, written as A, then a little cup B, it's the set of all elements that is either in A, B, or in both A and B. Also, we have the intersection of A and B. If we let A and B be sets, then the intersection of A and B, written A, and that's a little cap, B, is the set of all elements shared by A and B, or any element that is in both A and in B. Here you'll note that I used two Venn diagrams, but let's start with the one on the left. You can see I colored it in blue. That is the union of A and B. It's everything in A, B, or in both A and B. And the one on the right is A intersect B, and that is just the elements shared by A and B. It's represented by the overlap. And I have down at the bottom, note, A intersect B is always contained in A union B, or A intersect B is always a subset of A union B. Here are some more examples. If we have A being the set of integers 1, 2, 3, 4, 5, and then B being the set of positive odd integers less than 10, then A union B would be everything in both A and B, which is 1, 2, 3, 4, 5. And then B gives us 7 and 9. Although B also has 1, 3, and 5, we don't write them twice. So A union B is 1, 2, 3, 4, 5, 7, 9. And A intersect B is just 1, 3, 5. Those are the elements that are in both A and B. A few more examples. Say that we have A to be the set of integers and B to be equal to Q, which is the set of all rational numbers. Well, if that's the case, then A union B is Q, the set of rationals, and A intersect B is Z, the set of integers. Now, why? Because A union B is the elements that are contained within both of them, right? In either A or B or both. And that's Q because Q contains Z. Now, the intersection is just what do you find that is shared by these two sets, and that is Z because Z, again, is contained within Q. On the opposite end, if two sets A and B share no elements, then we say A and B are disjoint. And we can write A intersect B equals the empty set. Final example here. If we take the set A to be all x values such that x squared is less than or equal to 0, and B to be all x values such that x squared is equal to 4, well, we might simply state then that A is the set containing only 0, right? Because only 0 satisfies x squared less than or equal to 0. And B is the set containing positive or negative 2. So the union is negative 2, 0, 2. And A intersect B is the null set or the empty set. In other words, A and B are disjoint. So in what follows, we'll use the script U to denote the universal set or the set containing the union of all sets. Now this is for a particular problem. If you're given a question, the universal set changes dependent on that question. I gave two examples here. In the first one, I say, take three sets A, B, and C defined as such. Well, U is just the union of all three of those sets. There are no other sets involved with this question. So the universe of this set is 1, 2, 3, 4, 5, 7. In this next question, I have A to B, interesting set I chose, 1.1, 2.1, all the way to 11.1. Okay, it's only one set. If there is only one set in your problem, then the universe is that set. So here's that definition that I was speaking of. Let A and B be sets in U, the universal set. Then 1, the set of all elements not contained in A is called the complement of A. And it's written either A bar or A with a little C up top. I think we're going to stick with A bar because that's what the text does. But you might see it either way, depending on whether you Google or you look on YouTube for videos, okay? Just make sure that you understand the notation that you're using. And definition number 2 is the set of all elements contained in A, but not in B. And that's called the difference of sets A and B. And it's written A minus B. Okay, so be careful. You say A plus B when talking about sets. We have a union, which may be an analog to that, but we do have a difference. And A minus B would be the elements in A, but not in B. And B minus A is not the same as A minus B. B minus A would be the set of elements in B, but not in A. And then I have as a little note, you might recognize based on these definitions that another way to express the complement of A would be to say it's the universe minus A. And A minus B is equal to A intersect the complement of B. You can see here, I drew a few more Venn diagrams to correspond to the definitions on the previous slide. We have A bar, which is the complement of A. It's everything not in A that is in the universe. And you can see I colored in everything outside of A, which includes the part of B that is not intersecting A. And then A minus B is just this moon on the left because A is on the left, and it's the part of A not contained within B. And A minus B complement would be everything in A that is not in the complement of B. So everything in A that is not in the complement. The moon over here is in the complement of B. So A minus B complement would be the intersection. Now for a practical example, we're going to take U to be the set of integers, Z, and we're going to say A is 2Z and B is 3Z. 2Z is just the set of even integers. It's 2 times the set of integers, which is 0, plus or minus 2, plus or minus 4, and so on. 3Z, likewise, is the set of all integers multiplied by 3. So it's all multiples of 3. 0, plus or minus 3, plus or minus 6, and so on. Well, the universe is Z, and A is 2Z, so A complement is Z minus 2A. You can see that right here, or Z minus 2Z, I'm sorry. And what is that? Well, Z minus the even integers is just the odd integers, which I've written as plus or minus 1, 3, 5, etc. Now what about A minus B? A minus B is equal to all the elements that are in A that are not in B. Okay. In other words, you take the elements of A and then subtract out the elements that are in the intersection of A and B. So what is in the intersection of A and B? Well, I see here that this is multiples of 2, multiples of 3, so multiples of 6. So what this is going to be is all multiples of 2 that are not divisible by 6. If I was more human, I probably would have said all even numbers that are not divisible by 6, but I do math for a living. Now note, B minus A is not the same as A minus B. B minus A is all the elements in B that are not in A. And what this is now all multiples of, this time I have to write it as multiples, of 3 that are not divisible by 6. Because again, that is the intersection. of A and B.